So to continue from the last video, I'm just kind of going through the manual here, and this graph is basically saying, well, what if you take a sine wave and you can move it, right? You can translate it just like you did with this one, but instead of translating or moving it based on like by manipulating the equation based on just data. This one's using theta, right? It has no relationship to wavelength in this equation. With this equation, you have you're trying to figure out y. The value of y is equal to your amplitude, how high the sine wave is, times sine, and you're going to say, oh, well, this looks complicated, but it's going to be 2 pi, and there's some that's similar to this one, right? 2 pi, right? The first equation in the last video is right here, 2 pi times x over wavelength. So I like to think of this as, how are you describing the sine wave based on wavelength and the position of that wavelength? I mean, the position on the wavelength. Like, where is it at on the x-axis? Now we're using time, right? We have this new variable, two new variables, is 2 pi x over lambda, just like we have here. Sorry, yeah, x over lambda, but you're going to subtract t over, or little t over big T. Little t is just time, like time in seconds, and then period is also a unit that's in, or a dimension that's in seconds too. So seconds over seconds, they kind of cancel out on each other. So I guess an analogy for this is to say, well, you can think of a sine wave moving or propagating by time or by distance, right? By time or this is kind of like moving by distance. This is just one sine wave at one point in time, one instantaneous point in time. This is saying you're using a sine wave and moving it based on time. So that's kind of like saying, when we describe places, how far something is. Like, we often say this place is 5 miles away, or it can be 5 minutes away, right? You describe the same thing in two different ways, time and distance. So I don't know if I'm even if that even makes sense, but that's how I like to see what we're doing here. You're analyzing or describing a sine wave now based on time. And so, what is big T? Big T is the period of a wave motion. And in other words, a period is kind of like how many, well, let me take a step back. The period is the reciprocal of frequency. Frequency is often given in units of cycles per second, right? How many cycles can you have of this sine wave in 1 second? Period, on the other hand, is saying, well, how many, or how long does it take to go one full cycle, right? How long does it take? That's why big T is in seconds. How long will it take for one full cycle to go through? It could be more than a second, or it could be less than a second. It could be one. And that makes sense, because if T is 1, then F also has to be 1. Right? If T is 1, then F, of course, is the reciprocal, so on. Meaning that one cycle per, what the heck? 1 cycle per second, and this is 1 second. Remember, because again, the period is defined as how many cycles can you fit into 1 second. If frequency is 1, period is 1. If frequency is 1/2 cycles per second, that's like saying in 1 second you only have a half cycle. That means t must be 2. That means it takes 2 seconds for 1 full cycle, right? It's just a reciprocal. 1/2 over, sorry, 1 over 1/2 is going to be 2. Yeah, and then I think that's a lot of this is kind of like you kind of plug in the numbers and see what you get. And then to add on to this idea of a sine wave and the characteristic of light as a wave, you can also say that light has speed, right? Because light propagates, just like a moving object. So a moving object has speed, then so can light. And that equation is V equals wavelength over big T, sorry, or V equals wavelength times frequency. Right? They're the same thing because once again, period, big T, is the reciprocal of F. So, and V is sometimes given as C if you're talking about light, because light, the speed of light, is denoted by C, right? So C is the speed of light, and the speed of light is 3 times 10 to the 8th meters per second. So, okay, our first problem. You're gonna say our first problem is, let's read it. A series of waves of wavelength 100 centimeters, right? So you want to pick a point that you know looks kind of simple. I would pick, if I want to pick this point, I'd say from here to where does the cycle start again? From here to here. That's 100 centimeters. Or I can say from this point to this point is 100 centimeters, right? Because this is one kind of repeating unit, then another repeating unit, then another repeating unit. So 100 centimeters. It's traveling across a pond on which 3 corks, A, B, and C, are floating at a distance of these meters. So these corks they just go up and down. Just like light. When light's propagating, you have perpendicular fields, the electric and magnetic field, going up and down. This is sort of like a physical representation of light, of a transverse wave, I mean. So this A, you can imagine as the waves go from left to right, A is kind of just bobbing up and down. B could be potentially bobbing up and down too, unless it's at the what we call like the nodal point of a wave, meaning it's not really gonna well, actually, no, yeah, I mean, B is, forget I said all that. B can move up and down when the wave propagates from left to right. And then same with C. So, what's the question? At a given instant, a fixed post coincides with the wave minimum drop. Oh, that's just describing that, oh, this post coincides with this bottom part. So, like, this is the lowest you can go, right? Or the lowest of the wave. That's all that sentence says. What is the position of each cork relative to its equilibrium position? So what is the position of each cork relative to its equilibrium position? The answer, cork A is above equilibrium, because equilibrium is just at the line right here. B is at equilibrium. Right, it's kind of equilibrium can be viewed as like being in the middle, sort of the top and bottom. So A is above, B is at equilibrium, C is below because it's just right below the line right there. And we're talking about like what is the direction of motion of each quark? So this is something called instantaneous velocity. So it's kind of like when you're throwing an object, you might have learned this in physics, when you're throwing an object up, right when it reaches the top, the velocity is zero. Right instantaneously. Because it's about to switch. It's about to switch gears and go from it was traveling up and then now it's traveling down, right? When it changes direction, at that very point, v is zero. So kind of like with if you take that kind of concept, a is technically at this particular moment has a velocity of zero. So when things are at the top or the bottom, basically take home message, if it's at the top, the crest or the bottom, the very bottom of the trough, instantaneous velocity is zero. Or in other words, the direction of motion is none. There's no motion, so there's no direction. B, on the other hand, since the wave is kind of, if you try to imagine the wave going to the right, then B would kind of move down. The value of B would go down because when you shift, if you take this point where my mouse is and you shift it over, you're going to be at point B, right? This point moves over in the direction of propagation, and now you are below equilibrium. So this would be a downward motion. The direction of motion is down. For part C, you are basically gonna go up because since the wave is moving again to the right, you can imagine the next predictable place of this wave at point C would be somewhere over here, right? You're basically kind of saying this hill is moving to the right. So this hill is moving where C is. So motion would be going up. All right. We have time, I think, to talk about, actually no, I'll save this for the next video.